let's start the session. Okay, great. The very first talk for our conference in this session. So this session is about moving bits for the AI. Machine learning has become an increasingly important workload, and we have to innovate many communication protocols for it. So in this session, we're going to hear 4 amazing talks about our new efforts on optimizing the communication layer for AI. The first talk will be given by Yu Guan. He is now a senior software engineer at Alibaba Cloud. His research interests include AI infrastructure and the video streaming system. Today, he's going to give us a talk about his system Crux from Alibaba, which is going to talk about GPU-efficient communication scheduling for deep learning training. Welcome, Yu. Please start.
Thank you. Hello. Okay. Hello. Welcome to SIGCOMM'. I'm Yu Guan from Alibaba Cloud. In this very first talk, I'll introduce Crux, a communication scheduler of GPU clusters for multiple deep learning training jobs. In deep learning trainings, most GPU cluster providers try to serve multiple deep learning training jobs in one cluster. We call it multi-tenant GPU cluster. The goal of this design is to optimize GPU utilization, that is, to keep more GPUs working at all times. Sorry. Okay. Based on our production experience, high GPU utilization means the GPU clusters can do more computation and make more profits. However, the design of multi-tenant GPU cluster introduced a new problem, communication contention between jobs, and it significantly decreased GPU utilization. Now, let's see an example. Suppose we have a GPT model running in a GPU cluster. If we run a BERT model together, two jobs may share the same network links and compete for the network. We call this communication contention on network path. For this example, our experiment shows that the iteration time of GPT model is increased by 11%, and the GPU utilization is dropped by 9%. Contention can also happen inside a host. If 2 jobs occupy the GPUs from the same host, they may share the PCIe links and NV links, and then contention happens. So the question is communication contention frequent in production? The answer is yes. In our production-based investigation of over 2,000 GPU clusters, more than 39% of jobs ever experience communication contention with others, including contention on network switch, network links, and PCIe. So we say communication contention should be handled carefully. So why existing work does not help? First, most multi-tenant GPU clusters have job scheduler. The job scheduler locates each job to different hosts and try to avoid resource contention, including communication contention. However, as the number of jobs increases, communication contention can be reduced but cannot be completely avoided. So even the jobs are carefully located, we still need a communication scheduler to make path selection or assign higher priority to data flow of important jobs. It helps to further reduce communication contention. Unfortunately, existing communication schedulers focus on pure data transmission jobs. they try to minimize the completion time of each job or try to finish the data transmission before the deadline. So they are unaware of the flow pattern of deep learning training, like iterative traffic bursts. And they are also unaware of the of GPU utilization. So we need a communication scheduler for deep learning training jobs in a multi-tenant GPU cluster. Okay, to schedule the communication between jobs, first we should know what kind of job is more important. Let's see an example. Suppose we have two jobs running in the cluster. Job 1 occupies 8 GPU hosts, and job 2 occupies 2. So job 1 is 4 times larger than job 2. Intuitively, when job 1 experiences communication contention, more GPUs will be infected. So from this example, we know that a larger job should get higher priority. But what's the reason behind this? To answer the question, let's dive deeper into the deep learning training jobs. In deep learning training, communication and computation always depend on each other in one iteration. That is, a job must transfer a certain amount of data to unblock a certain amount of computation workload. When job 1 and 2 compete for the network, if the network transmits data of job 1 first, it can unblock much more GPU computation workload than job 2. So prioritizing job 1 can keep more GPUs working. So we get our first insight, we should prioritize larger jobs. Then we find that even two jobs occupy the same number of GPUs, their priorities may be still different. Based on our experiment, for example, a job with a longer computation time should be prioritized. And similarly, a job with a shorter communication time should be prioritized. Now we get the common point of all the above insights, that GPU computation intensive jobs are usually more important. Now, to quantify the importance of each job mathematically, we propose a new concept, GPU intensity. Generally, GPU intensity can be represented by dividing the computation workload W and the communication workload T. Basically, it describes how much computation is blocked by a certain amount of communication. And we prove that optimizing GPU utilization is equivalent to maximizing GPU intensity in communication scheduling. Details can be found in our paper. So based on GPU intensity, our key idea is to prioritize jobs with higher GPU intensity. In production GPU clusters, flow scheduling is usually achieved by path selection and priority assignment. So now I'll introduce the challenges and or solutions to prioritize GPU-intensive jobs in both two aspects. Now let's dive into the path selection. State-of-the-art GPU clusters usually provide multiple layer network switches. So there are multiple paths between GPUs. Although traditional hash routing can make a load balance between each network path, but when the number of jobs increases, communication contention is inevitable, regardless of path selection. So, given that the communication contention is inevitable, the challenge is, can we design a better path selection strategy to minimize GPU utilization loss in communication contention? Now, back to our key insight, GPU intensity. In fact, we cannot completely avoid all communication contention, But it is possible to avoid communication contention between high GPU intensity jobs. And we already showed that jobs with higher GPU intensity are usually more important in GPU utilization. Let's see our solution. Suppose there are 4 jobs running in one GPU cluster. First, we sort all jobs by their GPU intensity, and then we can select the most uncongested path for each job, one by one, from the highest GPU intensity one to the lowest. For example, we can select an idle path for job 2, and then select a different path to job 1 and job 3. As for job 4, there are no more idle paths, but we can still select the most uncongested one. We can see that this strategy does not avoid all communication contention, but it encourages high GPU intensity jobs to select different paths from each other. In this example, job 1 and 2 are assigned different paths. They are 2 high GPU intensity jobs. So this strategy can reduce most GPU utilization loss in contention. Now let's go to the second part, priority assignment. In production GPU cluster, data flow priority control is implemented by differentiated service code. Usually, it provides no more than 8 priority levels. And some of them are already reserved for special usage, like control message and network diagnosis. So we have only a few available priority levels for flow scheduling. However, the number of concurrent deep learning training jobs is much greater than the number of available priority levels. So it is impossible to assign a unique priority to each job based on its GPU intensity. And most jobs have to be assigned equal priority, leading to a random communication contention. So the challenge is how to compress this the priority assignment, but still try to differentiate jobs of different GPU intensities. We found that although there can be many concurrent jobs in a cluster, usually a job only has communication contention with some of them, not all other jobs. Just like this matrix, only red block means communication contention. So based on this insight, we can build a direct acyclic graph to describe the potential communication contention between jobs. An edge from A to B represents job A and B has communication contention, and job A has higher GPU intensity. Suppose we want to assign 3 priority levels to this job. Then the problem is transferred to finding the maximal 3 cut for this graph. That is, we split the graph into 3 subsets corresponding to 3 priority levels. We want to cut down as many edges as possible because for jobs with communication contention, it is more necessary to assign different priorities to them. To do this, we design an efficient dynamic programming algorithm to get the approximate solutions. We have built Crux in our production for daily communication scheduling. Our implementation needs to solve the following issues. The first problem is how to get the job information, including computation workload W and communication workload T, to compute GPU intensity I. To ensure a new job can be measured accurately, we always first assign the highest priority to it, to ensure it will not be affected by other jobs. Then we can measure its computation and communication workload using hardware monitoring tools. Due to time limit, please see the rest 2 issues in our paper. Our evaluation consists of 2 parts. our testbed evaluation runs models on GPUs to evaluate Crux. And our trace-based simulation uses our collected data set to evaluate Crux on larger scale GPU clusters. Our testbed evaluation runs 3 models: ResNet, BERT, and GPT. The left figure shows the job completion time, JCT, for each job, with and without Crux. We can see that Crux prioritized high GPU intensity jobs like GPT and BERT, with a small performance reduction on ResNet. And the red figure shows that such scheduling brings up to 13.9% of GPU utilization. Here's the result of our production trace-based simulation. Crux outperforms existing solutions and get higher GPU utilization. The data set used in our paper is now open source. We collect our information of our multi-tenant GPU clusters for 2 weeks in August 2023. The cluster consists of more than 800 hosts interconnected by a 3-layer CLOS network. And the dataset provides both topology information and job information. As far as we know, this is the first public multi-tenant GPU cluster dataset for large deep learning training. Feel free to click on our link and download our data. To summarize, first, we find that communication contention between deep learning training jobs should be handled carefully. Then we propose Crux, a communication scheduler for multiple deep learning training jobs, including path selection and priority assignment. Finally, we evaluate Crux based on both testbed evaluation and trace-based simulation. Thank you.
Any questions?
Hey, great talk. This is Zhang Yu from University of Washington. So I have a question. So do you have some...
Oh, okay. I see you.
Hi. Do you have some tasks which you cannot precisely get their GPU intensity? And how do you deal with that? And the second question is, what is the fundamental difference between your scheduling algorithm with some existing scheduling algorithm for processing scheduling in operating system? Thank you.
Okay, thanks for your question. For your first question, I think there are many existing hardware monitoring tools can accurately measure the GPU intensity. And because we only need to measure the computation workload and communication workload, we can use tools such as Insight or DCGM to do this. And for your second question, I think the difference between Crux and the existing communication scheduler is that first, we focus on the optimization of GPU utilization. And second, we consider some characteristics of deep learning training jobs. For example, we consider the traffic pattern of deep learning training job, and that is very different from previous applications. Thank you.
Hi. Hi.
Sorry, where are you? Oh, okay, thank you.
Okay. Hi, Guan Yu, really good talk. I'm Menghao Zhang from Beihao University. I have a question for the path collection. As you know, most AI network with no subscription. So if with no subscription, is there will be any path collection?
Pardon? What is subscription?
No subscription.
Can we explain this word?
One-to-one bandwidth.
Oh.
Over subscription, yeah.
Oh, okay.
So for network with no over subscription, is there be any path collection for multiple jobs?
For jobs of higher GPU intensity, if they do not need a large amount of network, the performance should be okay. But as far as we know, let me show you something. Based on our production GPU clusters, even the network bandwidth can be very high. We still have unevenly distributed traffic in the network. For example, we have hash polarization problem. So there are always some links are congested and other links are not congested. On the other side, recently we have more deep learning training jobs with higher communication consumptions. For example, we are focusing on some deep learning training with inter-host tensor parallel. And this inter-host tensor parallel is a very communication consumption operations. So I think communication scheduling, including path selection and priority assignment, is still important. Even the network bandwidth can be increased in the future. Thank you.
Let's take one last question. Yeah.
So I don't know if this is a sensible enough question to ask, but you deprioritize or you give lower prioritization for things that have to communicate a lot, right?
Can you speak slowly? Sorry.
Reduce the communication job, high communication job. Reduce.
So when there is high communication load, you reduce the priority.
So you are talking about fairness or something?
No, for your intensity measure,
yeah.
Your communication cost is in the denominator, right?
Sorry.
Offline.
Let's take it offline. Yeah, thank you. Okay.
Thank you for your question.